So this is the second energetics video, and in this one we're going to look at, we're going to mainly look at calculations using bond enthalpies. So in the first one we looked at why reactions were exothermic and why reactions were endothermic. And we saw that for an exothermic reaction, the energy absorbed when the old bonds are broken was less than the energy released when new bonds were made, and therefore overall energy is released and the temperature goes up. So the opposite was true for endothermic reactions. So let's see if we can work out what's in these gaps here. So energy when old bonds are broken, so when bonds are broken you need to put energy in to pull the atoms away from each other. So we're going to have absorbed, because you need to put the energy in to break the bonds. Energy absorbed when old bonds are broken is something than energy blank when new bonds are made. So, well, when new bonds are made, energy gets released. And if it's an endothermic reaction, overall energy is absorbed. So more energy is absorbed when the old bonds are broken than is released when the new bonds are made. So this one is going to be greater than the energy released when the new bonds are made. And for an endothermic reaction, the temperature goes down. So this is really just a recap of what we covered in the first video. This video is pretty much about the calculations. So we very quickly will run over the definitions. Enthalpy, hopefully you know, is heat energy. And enthalpy change, delta H, so change in heat energy. And a bond enthalpy, well, the bond enthalpy is the energy needed to break 1 mole of a bond. Now, if you're going on to do A level, you'll need to know a slightly more refined definition than that. But down here, you can see these are bond enthalpies. So in order to break 1 mole, if you like, of CH bonds, you need to put in 413 kilojoules. In order to break 1 mole of CC bonds, you need to put in 348 moles of energy. And in order to break a C double bond C, in other words, in order to turn it from CC into C and C, so in order to break both the bonds, you need to put in 614 kilojoules. Interesting, or potentially interesting, that the double bond doesn't require double the amount of energy to put in to break it, does it? Okay, significantly less than double. So that suggests that perhaps there's something slightly fishy going on with that second double bond. Anyway, that's a story we cover at A level. All you need to be aware of is that these values represent the amount of energy put in to break the bonds. Now, if the bonds are made, this is the energy that is released when the bonds are made. So we are going to use these values in order to calculate whether a reaction is exothermic or endothermic. So here we go. This is a typical exam question, although in an exam they might give you the structures of the chemicals involved. So here we've got methane, chlorine, and I'm going to just draw out very quickly the structures of the chemicals. and then on this side, so here's methane, and here's the chlorine, and then on the other side we've got CH3Cl, so there's CH3Cl, and we've got HCl. The writing's getting a bit better in terms of neatness. So you can see, and this is a reaction on the GCSE spec, that we've actually got a substitution reaction. One of the Cl's has substituted for the H, and the H has swapped in to form HCl. And you need to know that that's a substitution reaction. You also need to know the condition for that reaction, and that reaction only occurs when there's UV light present. It won't occur in the dark. So if you put chlorine and methane in a tube that's been wrapped up in aluminium foil, you won't get a reaction. However, if you take the foil off, you'll actually get quite an explosive reaction. So we covered in the first video that reactions start with bonds breaking and then finish with bonds making, and we're going to cover this in the same order now. So let's work out which bonds have been broken. So bonds broken. Now when you do these calculations, you can either choose to break all the bonds or just the bonds involved in the reaction. I'm going to use the method where we break all the bonds and then make all the bonds at the end. So bonds broken, well, we're going to break everything at the start. We're going to break 1, 2, 3, 4 CH bonds, and we're going to break 1 Cl bond. So here's 1 Cl bond. Right, now we can work out the amount of energy that's required to do that. So we've got 4 times 413, and the amount of energy required to break the Cl is 346. Okay, and if we add those numbers together, if you can just get a calculator to do this, you'll actually see that I'm using the wrong value. Well done. The Cl-Cl bond is in fact 243. So rather than start again, let's just keep going. 243, and if we get the calculator out, that comes to 1895 kilojoules. Right, now let's have a look at the bonds made. So what kind of bonds have we made here? Well, we've made 3 CH bonds, we've made 1 HCl bond, and we've made 1 CCl bond. So let's put that together in a calculation. So 3 times 413 plus 432 plus 346. And if we work that out on a calculator, assuming I've put the right values in, I get 2017. Now, they're asking us for the delta H. So the overall change, okay, you remember the order in which we do the reaction. So bonds get broken first, then they get made. So we have delta H equals breakup minus makeup. So 1895 minus 2017, and that comes to minus 122 kilojoules per mole. Or you could write kJ mole to the minus 1. And that's your final answer. Now, as it's negative, that tells us it's exothermic, which we'd expect, because more energy has been released when the new bonds were made than was absorbed when the old bonds were broken. And that's how you do one of the calculations. So let's try another one using a different reaction.